Okay, so today we are going to discuss one problem of finding equivalent mass, stiffness, and damping of the given system. So let's look at the system first. Find equivalent mass, stiffness, and damping. Okay, the given system is basically something like this, which is a two pulley system. This is the driver pulley, and mounted on the same shaft is the driven pulley. Okay, the driver pulley has a string attached to it with a mass. The mass is supported on a spring which is mounted to a rigid base. Let's call this mass as M and the spring as stiffness K. The moment of inertia of the driven pulley is I. Okay, and then we have the radius of the driver pulley and the driven pulley as R and 2R. Okay, so this driven pulley is attached to a damper system, which is nothing but a piston cylinder heat dissipation system. We are going to call the damping constant as C. Okay, alright, so this is the system that is given. We want to find the equivalent mass, stiffness, and damping of this system. We are going to start with first finding what are the independent degrees of freedom of this system. So, what do I mean by independent degrees of freedom? Basically, it means that this system, which will need at least these degrees of freedom to completely identify this system. So let's look at this. First degree of freedom is the movement of this mass in the translational position, that is x, and second is the movement of this disk in a rotational position, which is theta. Okay, we have not considered the movement of the other pulley because it is mounted on the same shaft, so it is not an independent degree of freedom. So basically there are two independent degrees of freedom. Now we are going to use the energy way to solve the problem. Okay, first find out the kinetic energy of the system. So kinetic energy of the system, let's represent it with T. T is equals to, you know that for the translational mass the kinetic energy is half mv square. So this is half m. V is the uh, velocity of the mass, which is dx by dt in our case. So let's call it as x dot, and that is square, plus what we have is the kinetic energy of the driven pulley. So that is going to be, or the disk, which is half I theta dot square. Okay, very simple. Instead of the translational mass, we have the rotational mass, which is also called as moment of inertia, and then we have got the degree of freedom, that is theta. Okay, so let's now what will happen is we want to represent this system in a single coordinate system. So let's see if we can represent theta in terms of r. Is there any relationship? Can we find something? So if you look at this small pulley, which is a driver pulley, the amount that the x will translate is dependent on the theta in the form of x is equals to r times theta. Okay, so you can say that theta is equals to x by r. Okay, so let's use this relationship and again rewrite the kinetic energy. T will be then equals to half mx dot square plus half I x dot divided by r square. So I've represented the theta in terms of x and r. Okay. Now in this case, you need to understand that you can also represent the x in terms of r, x in terms of theta, instead of doing what I have done. So it's one and the same basically. Okay. So for simplicity, let's simplify this equation. T will be then equals to half m plus I by r square into x dot square. So the term in the bracket is then our equivalent mass. Okay. Similarly, you can find out equivalent damping in the system. Okay, so let's find out equivalent damping in the system. For the damping, the work done is required. Okay, so work done from state number 1 to state number 2 is equals to integral of state number x1 to position x2, okay, times the force, the damping force. So I'm going to call it as force damping, okay, times the dy. Okay, so the total damping force is, then we can represent this damping force. One thing you need to understand, that this is the heat dissipated, so work is lost. Okay, so that's why this has to be a negative sign over here. So you can then represent this as negative x1 to x2. Force damping is nothing but cy dot, okay, times dy. So what is cy dot? Basically force is directly proportional to the velocity in that direction, so in the y direction. Okay, and so this proportionality you can remove by the damping constant c. Okay, so you are basically um, saying that the damping force is cy dot and then dy. Okay, so now you need to write down y in terms of theta. So y, you can say that y equals to 2r, that is the diameter of the radius of the bigger pulley, okay, times theta. Okay, so from this you can say that y equals to 2x. From our previous relationship of x and theta, we can come up with this y equals to 2x relationship. You can now replace y with x in here. Okay, so that will again be negative integral of x1 to x2, and this will be c times 2x dot d times 2x. Okay, so y is completely replaced with x now, and let's see what we arrive with. What you get is work done from 1 to 2 is equals to minus x1 to x2 for cx dot dx. Okay, and so the equivalent damping force is then ceq equals to 4c. Okay, so this part is the equivalent damping. Okay, so that's how we solve the problem.